So the next topic we started was recurrence and transients. And as we had said last time, this is because we want to classify the states depending on how often the chain returns to that state. Now, we have already decomposed the state into communication classes. And as we will see, this classification will behave very well with these communication classes. And this will give the most fundamental classification of states, as we will see. In particular, we'll be showing that both recurrence and transients are class properties, which means if I is recurrent and I communicates with J, then J is recurrent. Similarly, if I is transient and I communicates with J, then J is transient. So this will show that if one element of the class is recurrent, then if one state in the class in one communication class is recurrent, then all states in that communication class are recurrent. Similarly, if one state in a communication class is transient, then all the states of the communication class would be transient. And therefore, the communication classes would become either a recurrent communication class or a transient communication class. And this will lead to what is known as a canonical decomposition of the state space. So we'll talk about it when the time comes, but this would be a very important decomposition. Now, quickly recall, a state I is called recurrent if it returns to I with probability 1 in a finite number of steps. Otherwise, it is transient. So more formally, if remember the first return time to I is the first time the Markov chain returns to I. So starting from I, if the first return time is finite with probability 1, then we call I to be recurrent. So this means starting from I, we return to I in a finite number of steps with probability 1. On the other hand, starting from I, if there is a positive probability that it will never return to I, then we call it transient. Okay? So roughly speaking, a Markov chain starting from a recurrent state will definitely return to its initial state. But a Markov chain starting from a transient state may never return to its initial state. Now we have a further classification. This gives a classification of states. Either it is recurrent or it is transient. Now, a recurrent state can be further classified into positive recurrent and null recurrent as follows. A state I is called positive recurrent if its first return time has finite expectation when the Markov chain starts from I. So this is the expectation taken with respect to the probability Pi. So this means obviously it is recurrent, because if it is transient, then tau I1 takes the value infinity with positive probability, and therefore expectation under Pi, and therefore expectation under Pi has to be infinity. So obviously it cannot be transient. So positive recurrent is trivially recurrent. So what we are actually saying is that not only that the return time is finite with probability 1, its expectation is also finite. It's strongly recurrent. That's why it's called positive recurrent. Okay? Now, a state which is recurrent but not positive recurrent is called a null recurrent state. Now, in this case, this means that under Pi, the first return time is finite with probability 1, but it takes large values with reasonably high probability. In other words, first return time is typically large enough so that the expectation of the first return time becomes infinite. So that's what null recurrence means. So it does return to I, but it may take too long to return to I. On the other hand, positive recurrent means it returns to I and it also returns not too late. It returns quickly enough so that the first return time expectation under Pi is finite. Then we defined these sequences. So for each state j and k, and for each non-negative integer n, we define fjkn to be the probability under pj of the first return time to k equal to n. So this means this is the probability that starting from j, the Markov chain takes exactly n steps to reach k for the first time. Okay, so this is basically reaching k for the first time in n steps. So starting from j, the probability that the Markov chain takes exactly n steps to reach k for the first time is fnjk. Clearly, by definition, the first return time to k is bigger than or equal to 1. It's infimum over m bigger than or equal to 1 such that xm equals k. So therefore, it is by definition bigger than or equal to 1. It can be infinite, but infinity also is assumed to be bigger than or equal to 1 in this case. That's a standard convention, of course. So therefore, it definitely cannot be 0. Since it cannot be 0, if jk is 0 is always 0, whatever the states are. We define fjk to be the sum of fjkn's as n runs from 0 to infinity. Now this is basically the probability that starting from j, the first hitting time of k is finite. So this is the probability of hitting k in a finite number of steps starting from j. Okay. Now we made two easy observations. State I is recurrent if and only if fii equals 1. Now, what is fii? Fii is basically the probability of returning to I in a finite number of steps starting from I. If that is 1, this probability is 1, then only we say I is recurrent, right? So we call the definition of recurrence. So definition of recurrence is the first return time is finite with probability 1. Okay. Now, if jk is just probability under pj, tau k1 is finite. So fii therefore is probability under pi of the first return time to I being finite. And of course, if this is 1, then I is recurrent. That's why we have the first observation here. On the other hand, the second observation says, note that expectation under pi of the first return time to I is just this sum, n times probability under pi of the first return time equals n. So if the state is already recurrent, then of course this is equal to this. So this is a probability distribution as n runs from 0 to infinity. FIIN defines a probability distribution. It's basically the probability distribution of the first return time. Since that it's recurrent, it cannot be infinite. So therefore, it's a probability distribution. And this is the expectation, that this probability is equal to this probability. And therefore, this is the expectation. So therefore, a recurrent state is positive recurrent if and only if this sum is finite. Now note that in both cases, in this definition and also in this statement here, I started the sum from 0, but n equal to 0, we already know is not going to contribute because each fjkn when n equal to 0 is 0. Right? This is our observation. So therefore, we could have started this from 1 also. Now let's keep 0 here. No problem. Okay.